What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 4, Section 3, Fitting Linear Models to Data. Let's do it. Question number 1, describe what it means if there is a linear model breakdown when using a linear model. So what this means is that a linear model is, again, meant to represent a particular situation. Let's say it is how much money you're going to make per hour, right? So if we have an equation where you say y equals 15x, x might be the number of hours, 15 is the amount you're making per hour. So 10 hours, you'd make $150. 20 hours, you'd make $300. This model would break down in terms of negative values. For example, you don't really work negative hours. And if you worked, let's say we imagine -3 being plugged in, you'd somehow owe $45, but that doesn't really make sense in the scope of this linear model. So there's certain values that are outside the domain of this linear model as a representation of how much money you'll make in a total number of hours you work at $15 per hour. So that's what it means. There's a point at which in the domain where the model breaks down, it doesn't make sense. That's how you do it. Boom, done. What is extrapolation when using a linear model? It's when we have a linear model and it's predicting values within a certain domain and range, and then we try and apply that beyond the domain and range. So for example, let's say we've mapped something out for 10 years, right? Let's say from 2010 to 2020, and we've got that data, and then that creates a linear model. Then we try and use that to predict what's going to happen in 2030, 2040, beyond what the domain was used to calculate this linear regression model. So that's extrapolation, boom, done. So when we talk about a correlation coefficient, we're really saying how close is this to a nice linear model? And by the way, it can be a positive slope or a negative slope. When we talk about absolute value, right? +1 or -1 both indicate a linear relationship. It's just that one has a nice linear relationship with a positive slope, and the other one would be a negative slope. It just has a negative relationship. So for example, as the x values might go up, the y values then would tend to go down. And when the absolute value is closer to 1, we have the data more tightly packed together, forming a noticeable pattern. As it's closer to 0, that absolute value, then the data is going to be more scattered and there's less likely to be any sort of discernible pattern. A regression was run to determine whether there is a relationship between the diameter of a tree and the tree's age. The results of the regression are given. Use this to predict the age of a tree with diameter of 10 inches. So they give us these values. So what I'm going to do is I'm going to replace the A and B with these two values like so. Now, if we're trying to predict the age, which is represented as Y, we're going to plug 10 in for X, as 10 represents that diameter in inches. So there we have plugged 10 in for X. We're going to multiply that out. And we're going to do this, I think, without a calculator. I think we can handle this, minus 1.044. So then we've got the setup here. Now we're going to subtract like so. So then we got 10 minus 4 here, which is 6. 9 minus 0, which is 9. 2 minus 1, which is 1. And the decimal drops straight down. And then we got 6. So our answer is roughly 61.966 years. Boom, done. For this question, we're meant to plot the data and see if it forms a linear relationship. So let's go ahead and do that. So first we have 146, then we have 250, 359, 475, 5 100, and then 6 136. So to me, this does not look linear. This actually looks almost parabolic or potentially exponential. So I would say, no, this is not linear. Boom, done. So for this one, let's go ahead and plot the data points and see if it indeed represents a linear relationship. Got 1, 1, 3, 9, 5, 28, 7, 65, 9, 125, and 11, 216, maybe right here. Okay, so there's a nice approximation. Again, this doesn't look linear. This again looks like a parabola perhaps, or perhaps exponential growth, like a curve. So I would say for this question, once again, the answer is no, boom, done. So for this one, we're going to draw a scatter plot of the data, and then we're going to see if we can use that to make a prediction about 28 degrees. Then we're going to talk about whether that's interpolation or extrapolation. So first we have 1646, then we have 1850, then we have 2054, then we have 2555, and then we have 3062. So if we wanted to make an approximate linear model, it might look like this, like a nice regression line like so. So when we're talking about estimating the time for 28 degrees Fahrenheit, we want to look here and say, here's temperature, 28 degrees Fahrenheit. We're going to bring it up, and that hits about here on the line of best fit. And that's pretty darn close to 60. And again, we're talking about the y-axis time, so that would be an approximate 60 seconds. Now, the question is this interpolation or extrapolation? Well, the data value that we were testing, 28 degrees, is within the domain that has already been provided, right, from 16 to 30. So when we're going within the data values provided, this is called interpolation. However, if we were trying to match it up for like a temperature of 40 degrees or 50 degrees, that would be considered extrapolation. So 60 seconds, interpolation, boom, done. So for this question, we're meant to correlate this correlation coefficient with one of these graphs. Now, it's negative 0.89. That's pretty darn close to -1. That indicates a strong linear correlation, but a negative correlation, similar to like a slope, a negative slope, right, going down from left to right. So the one that would match up with this one would be C, figure 10C. So C would be the winner, boom, done. So for this question, we've got a correlation coefficient of negative 0.39. So that indicates a relatively weak relationship because it's pretty close to 0, but it is negative. So the two graphs that have weak linear correlations would be A and B, but which one is more negative, which one's more positive? It's a little hard to decipher, but I'm going to lean towards B. This looks like it has a little bit more of that negative slope, whereas this one might have a little bit more of a positive relationship. So B would be the answer. Boom, done. So for this question, we're meant to draw a line of best fit. And look, there's no exact way to do this, but I always like to think of threading a needle through all these points, kind of getting right in the middle. So just as an approximation, we're going to say something like this. So you see there's a nice balance of points above and below. It kind of seems to go right through the middle. That's what we want. Boom, done. So for this question, once again, we're creating a line of best fit, and we're going to approximate and just trying to get that line nicely through all these points. So let's say something like this. And again, I like to use that analogy of threading the needle, kind of going right through the heart of all these points. So there would be a nice approximate line of best fit. Boom, done. So for this question, we have import of wine for several years given in table 5, and then we're trying to determine whether or not this appears linear. So the first thing I'm going to do is I'm going to plot this data out just so you can see visually what it looks like. So this is roughly what the data looks like, and you can see that it would make sense that we could have some sort of a line of best fit that would look something like this. So when you input this data into a TI-84 calculator and run it through the linear regression, you see the following values for R, A, and B. So these are the values, and then if you put that in a linear equation to approximate this value of 12,000, it would look like this. Last but not least, we'd plug in 12,000 in for Y, and then we'd solve for X. Okay, so first step, we're going to add 813,800.6 to both sides. And last but not least, we're going to divide both sides by 409.5, and we get 2,016.6. So what this means is that it will exceed in the middle of 2016. So we say in the middle of 2016, boom, done. So for this question, we're going to use the set of data to create a linear regression, and I'm going to choose to use Desmos. You could also use a TI-84, but let's check it out using Desmos. So all I've done is I've looked up a linear regression kind of preset thing in Desmos. I went to it, and then I plugged in the X values and the corresponding Y values, and you see we get all the important values here. We get the correlation coefficient of 0.987, and then we get B1 and B0. So now using these values, I'll say R equals 0.987, and the linear regression is Y equals B1, which is given here, 1.640x plus that B0 or B null, which if we round it to the nearest thousandth is 13.800. So there's your R value, there's your linear regression, boom, done. For this question, once again, we're going to input this data into Desmos to get a linear regression, and then we're going to plug in the values and get the answer that way. So let's go to Desmos. So when we plug in all the values, we end up with this for R and these for the constant. So let's take that and write out the equation. So as we write this out, we've got an R value of negative 0.955, and then we have a linear equation of Y equals negative 0.893x, right? Just rounding to the nearest thousandth, plus that B null, which is 25.975. There's your answer. Boom, done. For this question, we're going to utilize Desmos to plug in the data and then create a linear regression model. So let's do that. Now, when we plug in the values here in the table like so, you see that we get all these nice constants that we need. We get the correlation coefficient B1, B0. So let's write out the linear equation. So we have R equaling negative 0.999. And then for the equation, it's Y equals that B1, which is negative 1.981, rounded to the nearest thousandth x, plus B null, which is 60.19, rounding that up to 7. There's your answer. Boom, done. For this question, once again, we're going to plug this into Desmos to create our linear regression model. So let's do that now. So for this one, we plugged in the values into Desmos and we get our R value B1, B0. So we're going to take that and write out the linear equation. So we got R equaling positive 0.998, a nice positive correlation coefficient, nice positive slope. And then we would get for our linear equation Y equals B1, which is 0.12 rounded up to the nearest thousandth, 1x plus B null, which is negative 38.841 rounding up. Again, we can make that instead of a plus negative, we can make it a minus, but there's your equation. Boom, done. So for this question, it starts out by saying graph f of x equals negative 2x minus 10. So I've already graphed this equation in Desmos, so I'm just going to plop it up here now. So here's what this graph looks like with a nice slope of negative 10. And then with these inputs, we're going to see if this matches. We're going to get the coordinates and plot them out and look at those points. So now as we plug these in, we're just going to plug them into the top function here, right? Negative 2 times negative 2 is 4, minus 10 is negative 6. And we're going to do the same with all of these values, plug and chug. So here are the coordinates, and we're going to plot those out just so you can see. So those are the points, and they lie right on that line, which looks awesome. Now we're going to use linear regression to verify the function. So I'm going to plug in these coordinates, and we're going to see what happens. So when we plug in all these values into the linear regression, check out what happens. The R value is a perfect -1 because this is a perfect line, right? These coordinates all make a perfect line. And we get those values of -2 for the slope and -10 for that y-intercept for that constant. Well, that's exactly what this function is, a slope of -2, a y-intercept of -10. So this indeed verifies the function. Boom, done. So for this question, we're looking at the profit over a 10-year period, right? And we're seeing the profit as the y values kind of dwindle, kind of drop. So what we're going to do is we're going to create a linear regression model using these data points, and then we're going to find the x-intercept to the nearest tenth. And the x-intercept occurs when the function value is set to 0, aka y is equal to 0. So let's do that now. So when we enter these data points, this is the result in terms of the constants for the linear regression. So let's plug that in. So we get y equals -11x plus 2088. And then it says find to the nearest tenth and interpret the x-intercept. Again, y is 0, so we're going to plug in 0 for y, and we get this. We're going to subtract 2088 from both sides, and then last but not least, we're going to divide by -11, and we get 189.8 to the nearest tenth. So what this value means, again, they said the x value is the number of units sold in hundreds. So it means 189.800 units being sold will give us a profit of 0. So you can say when selling 189, or sorry, it would be 18,980 because it's in the hundreds. So we multiply by 100. Units sold will give a profit of 0. There's your answer. Boom, done. For the following exercises, consider this scenario. The population of a city increased steadily over a 10-year span. These ordered pairs are population and the year, right? So first is population, and then the year is the second value, 2000, 2001, etc. Then it says use linear regression to determine a function y where the year depends on the population. So y represents the year, and let's do this. So plugging these values into our linear regression calculator on Desmos, we get the following values for R, B1, and B0. So this is enough to give us a nice linear equation. So we got y equals B1, and I'm going to round it just like they did in the book to the nearest 100,000th digit, like so. And then there's my y-intercept, 1985.41. That's how you do it. Boom, done. So once again, we're going to try and determine a function y, a linear function, based on this information. And this is the number of units sold in hundreds, so that's all this, and the profit in thousands, so these are the profit values. So we're going to plug it into Desmos and see what we get. So when we plug in these values here, this is what we get for the constants. So this is enough to get a nice linear equation. So using these constants, we get y equals 20.25x minus, or it could be plus negative, but minus 671.5. Boom, done. For this exercise, consider the profit of a company decreasing over a 10-year span, and this is the number of units sold, or the X values, and the profits in thousands are these values, 250, 225, and you see that's kind of decreasing. So we're going to plug these values into Desmos, create a linear regression model, and take it from there. So now when we plug in these values, this is the B1 and B's null values. That gives us the constants to make the linear equation. So let's do that now. So with these values, we get y equals negative 10.75 plus that B null of 742.5. So there is the linear function. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.